Wonderful. Yeah, so thank you so much for the introduction and the invitation. I'm Masha. I'm part of the Simulating Extreme Spacetimes collaboration. So we use the spec code that Manuela alluded to. So different from Einstein Toolkit, but always nice to have multiple codes for cross-comparison purposes and stuff like that. So today we'll talk about numerical relativity beyond general relativity and how we can use that to put Einstein to the test. Thank you to all of my co-authors and collaborators on this research effort, both in the Simulating Extreme Spacetimes collaboration and also in the LIGO-Virgo-CAGRA scientific collaboration. So our starting point is Einstein's theory of general relativity, summarized in the beautiful Einstein field equations. And these are wonderful. This is a wonderful way to describe lots of astrophysical phenomena, such as the orbit of the planet Mercury, the gravitational deflection of starlight, the orbital shrinking of the Hulse-Taylor pulsar, gravitational frame dragging. And so Chandrasekhar posed the question, why do you spend so much time testing GR? We know that the theory is right. In other words, why study these astrophysical systems for which GR is a wonderful description when we know that general relativity is the correct theory of gravity? However, nature isn't classical. So the universe is ultimately quantum mechanical. We know that we need quantum mechanics, for example, to describe atoms and particle physics. But general relativity is a classical theory of gravity that neither admits nor allows for or includes quantum corrections or any sort of quantum mechanics. And so there's this really big question in modern science of having a theory of quantum gravity that combines the fact that the universe is quantum mechanical with a theory of gravitation. And so this brings us to quantum gravity, which includes theories like string theory and loop quantum gravity. And so one of the main questions we have is, can we observe gravity beyond general relativity? Can we observe gravity at in the regime where Einstein's theory is no longer a viable description for what's physically going on in the system? So let's think about where we could look for gravity at its most extreme. So here's a plot from Tessa Baker et al., where we have the logarithm of gravitational potential increasing this way and the logarithm of curvature increasing this way for many astrophysical systems. So the solar system is actually a weak field regime, which lies over here. Then increasing in curvature and gravitational potential, we get systems like pulsars, which are a wonderful way to test general relativity. And all the way over here, we get neutron star and stellar mass black hole binaries. And so the claim is that these are really the best laboratory that we have for seeing gravity at its most extreme, to potentially see the regime where general relativity stops being a viable description of nature. And we need to reconcile with the fact that we need to have this ultimate theory of gravity that incorporates, for example, the fact that the universe is ultimately quantum mechanical. And so binary black hole and neutron star mergers really do probe gravity at its most extreme. So here's an animation from an NR simulation where really can pay attention to this ripple here, which corresponds to basically how highly space-time is distorted and disturbed. And you can see that especially during the merger phase, space-time becomes nonlinear, highly dynamical, really probing the strong field regime of gravity. So we really get to gravity that's highly nonlinear, highly dynamical, and in the strong field. And the fantastic thing about these systems is that they emit gravitational waves. So this is, not terribly new to everybody attending, but fundamentally, when we talk about gravitational wave morphology, we talk about the strain, which measures how much space-time is being stretched and squeezed. And we talk about three main stages of the merger, the in-spiral, the merger phase, and the ring-down phase. And it's really in this shaded green region near the merger phase where we need numerical relativity or solving the equations of space-time on the computer to tell us what the gravitational radiation looks like from these systems. And it's important to note that gravitational waves carry information about their origin. So whatever dynamics is happening near the source, the gravitational radiation that comes out is ultimately reflects, the physics that's going on. And so binary black hole and neutron star mergers are systems with extreme gravity, and we now can detect their gravitational waves with instruments such as LIGO, Virgo, and CAGRA. And so the idea is that the gravitational waves that we detect could potentially contain signatures of beyond GR astrophysics. And there have been over 90 gravitational wave detections so far, and even more to come. So this is, systems that we can now study. And so let's, for example, and a new era is actually coming, as Manuela alluded to in her talk, where we're going to have even more precise instruments, especially in this high curvature regime, such as Einstein telescope, Cosmic Explorer, and improvements to LIGO, Virgo, and CAGRA. And so putting all of this together, fundamentally, nature isn't classical. Our best laboratory to observe physics beyond general relativity, the regime where general relativity breaks down and stops being a viable theory of gravity, lies in stellar mass black holes and neutron stars. We can now study these systems with gravitational waves, and we'll have even more capabilities in the future. And so let's test general relativity with gravitational wave astronomy. Let's use our current and future gravitational wave observations to really put Einstein to the test. And so presently, LIGO, Virgo, and CAGRA do perform tests of general relativity with gravitational wave observations. So these mainly come in two flavors of tests. The first are what are known as null tests. So these come in three steps. First, you assume general relativity as your null hypothesis. So you make predictions using, for example, numerical relativity for what gravitational waves should look like in GR. You fit these predictions to gravitational wave data. So here's your actual data from the detector, and here's your best fit GR prediction. And you check that the residual that you have once you subtract off your best fit prediction, so here's the residual for the first LIGO event, for example, is consistent with noise. And indeed, it's found in GWTC3, the most recent LIGO, Virgo, CAGRA catalog, that indeed for general relativity, you would expect this dashed gray line. I'm not going to get too much into this figure, but this is what you would expect for general relativity, and this dashed gray line and this dashed blue, this blue line corresponds to observations from GWTC3. And I'm not going to go into this figure, but the important thing to note is that these curves are close enough to each other. And so in some sense, these null tests of general relativity have been successful. And there are also what are known as parameterized tests. So the in-spiral phase of a binary black hole merger, for example, when the black holes are going around each other, can be described in an expansion of the speed of light over v, the characteristic velocity of the system, over the speed of light squared, governed by some coefficients. And the important thing to note is that these coefficients have very precise values in general relativity for a given physical system. And so what we're going to do is we're going to look for deviations in these coefficients from their values in general relativity. And so here are results from GWTC3, where you have a variety of coefficients at various orders. So all the way from -1 Pn, where Pn is V over C squared, to higher orders. And here for each coefficient, I've drawn GR as this thick gray line. And here's the deviation from general relativity for each coefficient. And so the thing about this test, though, is that you vary the coefficients really one at a time, which isn't very physical, and you're missing the merger phase, which, as we've seen, is the most nonlinear, highly dynamical phase where potentially we could be on the edge of general relativity. And so we're moving into this new framework of model-dependent tests, where you take your gravitational wave data, you have predictions for what gravitational waves look like, not just in general relativity, but in a specific beyond GR theory of gravity that introduces corrections to general relativity. You find your best fit to the data, and you can ultimately use this to constrain or observe beyond GR effects. And so really the key is getting at these beyond GR predictions in a specific theory. So how do we produce gravitational wave predictions? Well, I don't need to tell everybody in this workshop, but ultimately we use Einstein, or rather standardly we use Einstein on the computer. And we use the field of numerical relativity, which is solving the equations governing the behavior of space-time on the computer. And so what we really want to produce these predictions. And so our ultimate goal in this program is going to be using the tools of numerical relativity to produce predictions for gravitational radiation in beyond GR theories of gravity. So not just general relativity, but beyond GR theories of gravity as well. And this is all done within the context of the Simulating Extreme Spacetimes collaboration with the SPEC code. And so really this is where numerical relativity beyond general relativity comes in, right? Our goal is to make these predictions so that we can ultimately constrain or observe beyond GR physics with these extreme gravity systems. So let's choose beyond GR theories to simulate. And we want these theories, you know, observing like true quantum mechanical effects is going to be difficult, but what we want is to think about theories that do have motivations in the fact that we need to have some ultimate quantum theory of gravity. And so we think about what are known as beyond GR effective field theories. So these are classical theories that modify the action of general relativity through the inclusion of higher curvature corrections. So basically what we say is that general relativity, shown by the Einstein-Hilbert action right here, is just the first term in an expansion of higher and higher orders in curvature. So this is the Einstein-Hilbert action, and then here are my higher curvature corrections. And script r squared, for example, refers to any curvature quantity that you can come up with that's quadratic in curvature. So for example, you can think about like Ricci tensor contracted with itself, Ricci scalar squared, Riemann tensor contracted with itself, really any combination of curvature terms that end up giving you something quadratic in curvature, and similarly for the script r cubed. And this expansion is governed by some length scale below which these beyond GR effects become important. So if this length scale is 0, you've recovered general relativity. And if this length scale is non-zero, then basically what you say is that below this length scale, this is where I need to include these beyond GR effects. And the idea is that these quadratic curvature terms in specific theories have motivations in quantum gravity theories, such as, for example, string theory or loop quantum gravity. And so in this case, we're going to think about quadratic gravity theories, which go up to second order in curvature. So why these theories? Well, first, they're well motivated by beyond GR physics. There are wonderful review papers that talk about the theories we're going to discuss and how they relate to high energy physics. Deviations from general relativity are small in this case. You do include the Einstein-Hilbert action here, but the fact that this, these are high curvature terms mean that they really only become important in high curvature regimes. So you pass, for example, all of the solar system tests when you're in a low curvature regime. And this length scale can, in a sense, be as small as you want it to be. Including 0. And also they introduce new phenomenology, and ultimately astronomy and astrophysics need to be backed up by theory. And so these theories, as we'll see for black holes, neutron stars, they introduce new phenomenology into the system, hence providing an avenue for testing general relativity. And so the two specific theories we're going to talk about are dynamical Chern-Simons gravity, which is a quadratic theory of gravity. And I'll talk about this in a little bit more detail towards the end of the talk. The thing about dynamical Chern-Simons gravity is that it has general relativity right here, a quadratic curvature piece here in this Kontriagin density, the dual of Riemann contracted with itself. This length scale governing this, the fact that we're working in an effective field theory, right? This is the length scale below which beyond GR effects become important. And to make this theory dynamical, you need to couple this to a scalar field. And have a kinetic term for the scalar field in order to actually introduce dynamics. And for our purposes, we need to know that just black holes, neutron stars, and orbital dynamics are modified in this theory. So this is a wonderful theory to use to test GR in a model-dependent way. And similarly, we're going to talk about Einstein dilaton Gauss-Bonnet gravity, where it has a different quadratic curvature term known as the Gauss-Bonnet scalar. But again, you have general relativity. You have a length scale square root of alpha, which governs the strength of beyond GR modifications. And again, you have a scalar field in the theory to make it dynamical. And both of these theories have ties to quantum gravity theories, such as string theory and loop quantum gravity. So even though we're adding classical terms to the action, there are ways to think about them in a high energy theory context. And again, black holes, neutron stars, orbital dynamics are modified in this theory. And so at the end of this section, I'm going to talk about the actual kind of formalism that we use. I'm going to talk about results first, just to keep things interesting. But our method that we use is known as an order reduction scheme, where in order to ensure a well-posed initial value problem, what we do is we say, well, I know how to simulate a system in general relativity. Let me then perturb around general relativity to get a well-posed initial value formalism and get results for what the leading order Einstein dilaton Gauss-Bonnet or dynamical Twin-Simons gravity correction is to my spacetime metric, which then allows you to correct the gravitational radiation. And I'll talk about this more towards the end as a bonus for people who are interested in it. But if you really want to get technical, I'll point you to these 7 papers that really detail this formalism under results. And so we need to choose astrophysical parameters to simulate, including masses, a ratio between the 2 masses and 2 black hole spins. The wonderful thing about numerical relativity is that it's scale invariant. So you do one simulation, it's valid for stellar mass black holes, supermassive black holes if you want. We're really looking at a high curvature regime, so we want lower mass black holes. And the other thing about this scheme, this order reduction scheme, is that this beyond GR length scale scales out. So I only need to do one simulation for a set of astrophysical parameters, a set of black hole parameters, and then I can turn on in post-processing the strength of beyond GR modifications that I want. So this is great because you only need to do, like 1,000 simulations to build an effective surrogate model in the same way as in GR, we do like 1,000 simulations to build a very good surrogate model. So for our first simulation, we chose parameters consistent with GW 150914, the first LIGO detection. So a system with effective spin 0, but having spins on the black holes, and a mass ratio around 1.2. And again, this is scale invariant, but when I introduce back a mass scale to talk about L as a length scale with physical units, I'm going to use M equals 68, going along with this first LIGO detection. But of course, the lower mass your system, the higher curvature of a regime you're probing. So here are our results, and they're ready to use in a sense. So here's the gravitational radiation as a function of time for the simulation in dynamical Twin-Simons gravity. I've scaled out the total mass of the system, but here's what it looks like for various values of this coupling parameter. So for L equals 0, this corresponds to general relativity. This is this dashed black line. And as you can see, as I turn up the value of L, I get deviations both on the amplitude and the phase. And here I really am focusing on modifications to the merger piece of the waveform, because this is really the region that we can only get at with numerical relativity because of the high nonlinearity in the partial differential equations governing the system. There are other ways to think about beyond GR modifications to the ring down and in spiral portion, but here we're really focused on the merger phase. And similarly, well, I can put in a mass scale if I want. And for this system with this mass, by eye, if you want to differentiate between the GR and beyond GR waveforms as a function of the coupling parameter, it's around 10 kilometers that you can really differentiate them by eye, which corresponds to the black hole horizon scale in the problem, and is 7 orders of magnitude better than any sort of constraint that you can get, for example, from the solar system. And here are results for Einstein, dilaton, Gauss, Bonnet gravity, again with the total mass scaled out. And GR is in the dashed black line. And as I ramp on, as I sort of introduce larger and larger values of this beyond GR coupling parameter, I see modifications to the amplitude and phase of the system. And so in a sense, these are ready for use for DCS and EDGV. And the idea is we're going to do a lot of these simulations and cover the parameter space, and then we'll be able to do model-dependent tests of general relativity, where we take a specific theory and compare it against gravitational wave data from the detector, rather than just comparing GR or some parameterized modifications to the in-spiral phase. And so, you know, these are ready for use, and I've started working with colleagues in the LIGO-Virgo collaboration who work in the field of data analysis to think about how we can use these for model-dependent tests. And one important study we're working on right now with me, Max, EC, Wolfar, and Katerina Shaltzeanu, is this question of how does gravitational wave analysis respond to beyond GR astrophysics. So we have these waveforms, beyond GR waveforms, let's say in dynamical Chern-Simons gravity, which we used for this study, with various values of the coupling parameter. And what we want to know is that if we put these through standard LIGO, Virgo, CAGRA data analysis pipelines, in other words, if we say, you know, this is the signal that I've received in my detector, what could I currently infer from it using standard data analysis pipelines, including Bayes wave, which is a morphology independent analysis that does not assume GR, and it makes minimal assumptions. It says that the signal just comes from a distinct point in the sky, it travels at the speed of light, and it contains no extra gravitational wave polarizations. And then we're also going to use Bilby, which is a model-dependent parameter estimation framework that uses general relativity waveforms and compares them against the data that we see. So in this case, we're going to be taking our beyond GR data and comparing it against a bunch of GR waveforms using this full parameter estimation pipeline. And this is an important question because suppose we were doing, we injected our beyond GR signal into a GR parameter estimation pipeline. If we found a matching GR waveform, this would basically tell us that there's a degeneracy between our beyond GR signal and some point in GR parameter space. So in other words, if I have a manifold here in waveform space corresponding to GR waveforms on this manifold, if I was in a very ideal situation, any sort of beyond GR effects that I introduce would take me off of this manifold to a solution not found in GR. But pathologically, if I had a degeneracy, I would just be moving along the manifold of GR solutions and just getting a change in parameters. So in other words, my beyond GR effects would be able to masquerade as GR. So I'd never really be able to test GR in this framework. But here are our results. So here, going down the columns are different signal to noise ratios for our injections. Going down the rows, I meant. Going across the columns, here are different values for the beyond GR coupling parameter. So this column corresponds to L equals 0, which is general relativity. And here I'm introducing larger and larger values of the coupling parameter. And so in dashed black, we have our injected waveform. In blue is the confidence interval from our morphology independent analysis. And what we see is that this analysis is able to fully reconstruct our injected beyond GR signal. So in other words, our morphology independent analysis will be able to pull out these beyond GR signals from the data. The pink region is the GR analysis performed on our beyond GR signals. And what we see is that if we compute the residual between the best fit GR waveform and our injected waveform, we get for larger signal to noise ratios and larger values of the beyond GR coupling parameter, so the strength of the beyond GR modification, we get a residual that is not consistent with 0, and in fact is convergent, let's say, with signal to noise ratio. So in other words, and we can get quantitative about this, thinking about actually computing mismatches, but the ultimate takeaway, so if you want to get quantitative, I can show you these results, but the ultimate takeaway is that a morphology independent analysis can find and reproduce our beyond GR injections, while a model-dependent GR-based parameter estimation pipeline cannot. So in other words, our beyond GR waveforms cannot mask as GR waveforms, but can be found in the data, which is exciting because there's this lack of degeneracy, and so potentially you could, fully perform these model-dependent tests of general relativity in these specific theories. And again, this is exciting because a whole new era of gravitational wave astronomy is coming. We're going to get higher signal to noise ratios, being able to do more find gravitational waves with more precision. And our ultimate goal here is to take gravitational wave data, combine it with our beyond GR predictions and specific theories, run it through a pipeline where now we fit our beyond GR waveforms to the data and use this to constrain or observe beyond GR effects to do parameter estimation on the system, including a beyond GR length scale. And so we really want to build a beyond GR predictions catalog in the same way that within SXS in 2019, we released a catalog. Okay, so now for those interested on how we actually do this, we started like 5 minutes late for me, so I've rehearsed around like 7 minutes for this. So, if it's okay, I'll just quickly go through this. So in numerical relativity, our goal is to produce beyond GR waveforms, so numerical binary black hole waveforms in theories beyond general relativity. So numerical relativity in 2 minutes. So Manuela already alluded to this. When you take GR, you're used to thinking of the space-time metric as a 4-dimensional quantity. What we do in numerical relativity is that we slice up space-time into a set of spatial slices with a time-like vector moving us between the slices. So here we have labeled each slice with a certain time, or just like a time label. We have a spatial metric on each slice, and then we move from slice to slice using a unit time-like normal vector. And Manuela showed this picture before, but moving from slice to slice, you have a lapse function measuring proper time, and then your coordinates shift according to a shift function. But what's important for us to note is that the equations on each slice are elliptic, and the equations that take us from slice to slice when we solve, for example, the Einstein field equations are hyperbolic. So it's important to have what's known as a well-posed initial value problem. In other words, if I introduce small modifications to my data on a slice, then those modifications won't grow exponentially away from the result I would get from, a data point, or rather a point on the slice close to that. So in other words, for us numerical relativists, this basically means that your numerical errors won't lead to super exponential blow up, let's say, in your results. So it's important for us to have a well-posed initial value problem. Dynamical Chern-Simons gravity and Einstein-Dilaton-Gauss-Bonnet gravity. In DCS, if you compute the actual equations of motion that you get, so you vary the action, you end up with third derivatives of the metric in your equations of motion, whereas GR has only second derivatives. And so this asks a question about well-posedness. So can I actually have a well-posed initial value problem in this theory? And similar work has been done in Einstein-Dilaton-Gauss-Bonnet gravity as well. So there's this problem of potentially of well-posedness. However, we do know that GR is well-posed. So what we can do is we can perturb around general relativity. I can say that my spacetime metric is a GR metric plus modifications governed by some perturbation parameter. And similarly for the scalar fields in this theory. And so we end up with this cartoon, right? It's always useful to look at our picture rather than equations. So in pictorial form, what we do is we start with a GR binary black hole background at 0th order. This is something that we've known for almost 2 decades now how to simulate. The curvature of this background is going to source the leading order dynamical Chern-Simons gravity or Einstein-Dilaton-Gauss-Bonnet gravity correction to my scalar field. And then this scalar field plus this curvature is going to source the leading order correction to the metric, as the spacetime metric. And this is what's going to give me by my beyond GR waveforms, right? Once I get this correction to the metric. And what's important to note is we're really including this coupling to the curvature. This isn't just Einstein plus a scalar field. Here we really are introducing these higher curvature corrections. So we are working in this beyond GR theory of gravity. And so we've done this, we've gone to second order in our simulations. And as I showed before, we computed these kind of leading order modified waveforms in DCS and EDGB. If you want to know more details, 2017, we did this for the leading order scalar field. So this first order step. And we use basically a first order hyperbolic setup for the scalar field with constraint damping, adding in the dynamical Chern-Simons gravity terms. Helvey Witek et al. Did this for EDGB in 2018. Going to the next order for well-posed metric evolution, we took the generalized harmonic formalism, took a first order decomposition approach, added in constraint damping terms, and to get the DCS correction to the metric, you basically take these and you perturb them. So you take the generalized harmonic equations of GR, you perturb them, and then you get an evolution equation for your correction to the metric that does guarantee strong hyperbolicity. So I've thrown a lot of equations here. If you are interested in these equations, this is just kind of a bonus term. For initial data, we do a perturbation of the extended conformal thin sandwich approach, collecting gravitational radiation. We linearize the Newman-Penrose scalar, and we reintroduce a regime of validity where we basically say, I still need to be in a perturbative regime. My leading order correction to the metric cannot be greater than my spacetime metric because then I'm not in a perturbative regime. And so we get what's known as an instantaneous regime of validity, where as a function of time, you get allowed values for your beyond GR coupling parameter such that you're still in a perturbative regime. And this is all in the spectral Einstein code, your guaranteed exponential convergence. We only consider the merger phase so that we don't run into any sort of secular effects during the in spiral by virtue of evolving on a GR background rather than solving the full problem. So again, we focus on the merger phase. And again, these are ready for use. So I know I kind of whizzed through that, but the whole point there was if you're interested in any of this mathematical formalism, please reach out to me, please read the papers. But for the rest of you, I hope that the kind of astrophysical part of the talk was at least interesting. So to summarize, general relativity is a beautiful classical theory of gravity. Nature isn't classical. Binary black holes and neutron star mergers are our best chance to observe beyond GR astrophysics. Presently, null and parameterized tests are being performed with gravitational wave observations, but the new thing that we want to do is perform model-dependent tests of GR with gravitational wave astronomy, picking specific theories, simulating binary black hole mergers in these theories, and then comparing them to detector data. So we have generated the first beyond GR merger gravitational waveforms. We've shown that we can analyze them with present gravitational wave astronomy tools, picking out these beyond GR waveforms in the data and the fact that they're non-degenerate with GR. Future goals include making a whole catalog, and it's exciting for the coming decades because our ability to test GR will only increase. So that's my talk. Again, I shifted it 5 minutes because we started 5 minutes late for me. But again, if you're interested in the mathematical formalism I alluded to just in the last 5 minutes of the talk, please come talk to me or it's all in the papers if you're interested in the technical side of things. But again, I hope that the first kind of astrophysics part that we talked about was at least interesting. Yes, thank you. And that's the end of my talk.
Can you hear me okay, Masha?
Yes, yes.
Wonderful. Thank you so much for that wonderful overview. Yeah, so we actually have about 4 minutes for questions in case we have anyone live. Sorry, not live, but in person. Everyone's live. Yeah.
I guess I just want to clarify if that beyond GR waveforms, there's no way to tell the difference, even if we have an accumulation.
Yeah. So did you hear that?
I didn't fully get that.
Okay. So the question was, if there is a degeneracy beyond, between the beyond GR and the GR waveforms, is there no hope? Is that okay? Yeah. Is there no hope for even if we had a catalog, let's say, of potentially degenerate waveforms?
Yeah, so that's a great question. So really, when we did this investigation, we did it for basically one point in parameter space. So we said we have some GR solution here for GW 150914, let's say. We introduced our beyond GR modifications. We found that, because we couldn't fully reproduce it with GR waveforms, that it does take us off of this manifold of GR solutions in waveform space. So here, when I say waveform space, I mean that, this is a very multi-dimensional space where each dimension, for example, could correspond to, let's say, the amplitude at some gravitational wave frequency. Now, if I had degeneracy, basically for full degeneracy, let's say, for any point in parameter space, I would just be moving along this manifold. And so when I do parameter estimation there, I would be basically doing just parameter estimation on this point, let's say. If my true signal, were really, some DCF or some dynamical Trin-Simons or Einstein-Dilaton-Gauss-Bonnet gravity signal here, my GR parameter estimation waveforms were just pick it up okay, here we are in GR parameter space. I'm going to get a bias in the recovered astrophysical parameters of the system. The inferred spins and masses aren't going to be correct because I haven't included beyond GR effects. But you would obtain, let's say, comparable likelihoods in this case. Now, we've done this for one physical system. There's the question of, okay, let's say that this system that we considered was degenerate. In other words, we got the same level of confidence in the GR parameter estimation pipeline as we got in the morphology independent analysis. In that case, It would be instructive to potentially look at other sets of parameters. So let's say we had something like different spins. Let's say we had a different mass ratio where you could, yeah, something like different spins, different mass ratio. Maybe there's a point in binary black hole parameter space where these things are non-degenerate. The DCS manifold of solutions and the GR manifold of solutions, surely they have some intersections. And so, yeah, in that case, it would be instructive to look at other points in parameter space. For our GW150914 like simulation, we, happily found that it wasn't degenerate. So if we had such a signal in nature, we'd be able to, in a sense, pick up on it because our morphology independent analysis and GR parameter estimation results would be different. And so we'd say, well, there's something there, right? There's some additional physics there. There's some additional signal there that GR cannot reproduce. And so it's tricky to make a global statement right now because we haven't covered every point in binary black hole parameter space, but at least for the simulation that we've considered, we don't get this, masquerading as GR.